Welcome back, everybody. This is the final episode. This is the final lecture. In this lecture today, we're going to talk about the universe as a whole, its beginning, and possibilities for its end. It's pretty deep, dark, heavy stuff. So this is Earth and Space Science 102, and I'm Stephanie Welch. Let's start off by putting a little bit of a definition to a term that you've probably heard of before, at least maybe because there's a TV show named after it. Let's go ahead and define what the Big Bang Theory is. Now, the Big Bang Theory is probably the worst name that could have been associated with this theory, but it all sort of started out as a joke. So by the 1920s, some of the astronomers of that time, namely people like, again, Hubble, were coming to this idea that the universe hasn't just remained still. It hasn't remained static throughout time. It's actually changing, and it's expanding over time. His observations in red-shifting galaxies, this idea that the longer wavelengths of light were being stretched out behind galaxies as they were all moving away from us, is what led Hubble to this theory. And it caught on, and by the 1920s and into the 1930s and beyond, the 1940s and so on, there was pretty strong observational evidence for this idea that the universe hasn't just remained constant, hasn't remained unchanged over time, that it's dynamic, that it's changing over time, and it's actually expanding over time. Now, as with any branch of science and any new idea that would come out in any branch of science, there was a lot of backlash to this idea. Mainly people like Fred Hoyle, who's a British astronomer of the time in the 1940s, were strong advocates of this idea that the universe hasn't really changed over time, that it was static, it was still, that there was no expansion between galaxies taking place. So Fred Hoyle was on the BBC radio in the 1940s, actually in 1949, and in a way he was sort of trying to make fun of this idea, of this expanding universe idea, and he called it, that Big Bang Theory whatever idea, and the name caught on. So the reason why this doesn't really make a whole lot of sense is, first and foremost, because if you're trying to explain the origin of the universe with the name of this theory, then the Big Bang Theory doesn't make sense, because sound doesn't travel through space. So the universe did not start off with a bang, at least not an audible bang. So that's a part of the issue here. And the second is that it doesn't really explain what is proposed by this theory. Something like maybe the expanding universe theory would certainly make a lot more sense. The Big Bang Theory is the idea that the universe started off as something incredibly small and hot and dense, made up of pure energy, and that it has expanded out to the point that we have now, with hundreds of billions of stars in the Milky Way galaxy and hundreds of billions of galaxies in the observable universe. And this idea includes the idea that it's going to continue to expand into the future. So today's lecture is going to be all about this idea of how did it start, how will it end, and what are the big achievements along the way in the whole history of the universe. So using the expansion between galaxies that Hubble first noted in his early observations, we can even come up with an age of the universe. And the way we do this is by looking at the rate in which expansion takes place, rewinding the clock, and rewinding it back to a point where all of the matter in the universe was in the same place at the same time. And if you run that series of calculations, you get a number just under 14 billion years. And that is the widely accepted scientific age of the universe. Far, far older than the age of the Earth and the age of our solar system. About 4 times longer than the age of the Earth and the age of the solar system. If you want to put a very specific number on it, the current observational evidence would narrow that down to about 13.82 billion years. That's how long the universe has been around. That's how long it has been expanding out to the position that we have it now. Now, when we look out into space, something really weird happens that we discussed originally when we were talking about the speed of light and how light has to travel across immense distances in space. Because space is a really big place, the universe is a really big place, and light has to travel across incredibly long distances, that light has a beginning, a point of origin, and it's traveled over time to get to us. Because it takes time to travel to us, because light does travel at a very, very ridiculously fast but finite speed, then we are not actually seeing that object as it is currently today in our time. We're seeing it as it was when the light first left that object. And this becomes most apparent when you look out into the furthest reaches of the cosmos, when you look out into the furthest reaches of space. When we try to look back to the very, very, very edge of the observable universe, which is a radius in any distance away from Earth as we look out, we can only look out to the same distance as the age of the universe. If the universe is 13.82 billion years old, then we can only see out in any direction 13.82 billion light years away. And when we do, we are looking back in time to the moment of the Big Bang. And we can see the remnant energy from that event in something called the cosmic microwave background radiation. And that's something I'll talk about a little bit more in just a minute. So this means that our view of the universe is undoubtedly very, very selective to where we are in our perspective and very jaded from that perspective. We can only see out in any direction in what could be an infinite universe, or a universe in which we're just sort of shuffled off into sort of one corner, certainly not at the center of the universe. We're looking out in all directions only up to that point. So from this point of view, you could be anywhere in the universe and you can see out effectively out to the beginning of time, to the beginning approximately 14 billion light years away, and think that you're in the center of the universe. So there is really no evidence to suggest that we are in the center of the universe, but everybody gets to be in the center of their observable universe, because this is based on your own individual perspective, looking out as far as you can see and only being able to see back to the beginning of time. So we don't exactly know where we are in the universe. We don't know how common the sort of environment in the universe that we are in is compared to the rest of the universe. The distribution between sort of what we would call normal matter and dark matter, we can't really know these things. And it definitely calls into question any kind of theories that we can come up with about the continued evolution of the universe and how much expansion is going to take place and all of these other things. It's going to be very much jaded by our notion that we are limited by our perspective. Now, just as we're limited by our perspective and this idea that we are seeing backwards in time, that's also somewhat of an advantage, because at least it allows us to really definitively prove the Big Bang Theory. And one of the greatest proofs for the Big Bang Theory is the idea that as we look out from our center of the observable universe and we look out into more and more and more distant reaches of the cosmos, we can tell we're definitely looking back in time and that some expansion of the universe has taken place, because as we look out, first we see hotter, denser, more massive stars, the stars that were very typical of the early days in the universe when the universe was a lot smaller and denser, and those high mass stars would have been more common. And then as we look even further on past that, past the reaches of the furthest galaxy, we see this slight warm radiation permeating everything. We see effectively this wall at the very, very end of the observable universe that is the beginning of time itself. And this wall that you end up reaching is called the cosmic microwave background radiation. And this is remnant heat essentially from the early inflation of the universe, from the early expansion of the universe, all from a single point source. So we're looking back to really just the first few seconds after the birth of the universe when we see back to this cosmic microwave background radiation. Not only that, but just a few years ago, back in 2011, we were able to finally detect these waves within the cosmic microwave background radiation, and those waves are remnant from the early expansion of the universe and the early inflation itself. And it gave us even more strong observational evidence for this idea that the universe is expanding from a single point source. So the history of the universe is something that not only can we speculate on, but we can observe directly because we've got this cool ability to look back in time. And the finite speed of light gives us that ability to look back in time. It's really cool in that respect. Not knowing how things in the distant universe are today is the limitation of that. But all we have is what's provided to us. So that's the give and take of our perspective on the universe. Now, the main thing that I want to cover today is a little bit of a synopsis, a little taste of the history of the universe, going back from the very beginning when the universe started to inflate like a balloon and expand long before the first stars formed, to the formation of the early generation of stars, to the later generation of stars like our own, and taking us forward in time to the very present. So looking over approximately 14 billion years or 13.82 billion years of time. Now, I'm going to do this by going back to the beginning of time, and I'm going to walk you through this. But what I wanted to start you off with was a really, really cool way of conceptualizing this view of time, this immense, staggering amount of time, by compressing it into a single calendar year. The TV show Cosmos in 2014 did this by laying out on a calendar effectively 13.82 billion years of time, compressing it into a single calendar year, and having the first day of the year, January 1st, be the moment of the Big Bang, and December 31st be where we are now, and the last second of the last day of the calendar. So I think you'll appreciate this perspective, and it'll take you through a little bit more of a brief explanation of the big events that have happened over time. And most importantly, this will allow you to see how much time 14 billion years is compared to just the last 6,000 years on Earth, for instance. What a difference in time we're talking about. So I hope you enjoyed the little video clip. So I hope you enjoyed that perspective on time. I just really like how it allows you to kind of break down all these big events. And probably the most important thing to remember is that in the view of time across the entire universe, the formation of our single star, our sun, and our planet and everything that's happened in the history of life on Earth, that's only happened in a quarter of all of the time in the universe. So I thought I would kind of concentrate in on especially some of those early events in the history of the universe. And the way I'm going to do this is using this image out of your textbook, out of chapter 16 in your textbook, where we have both this overall idea of inflation taking place and expansion of the universe. You can see that in this image. You can see how temperatures decline as all of this matter and all of this energy is spread out into a greater and greater and greater amount of space, and how time is going to progress and how all of these events are going to progress because of the relationship between the expansion of the universe and the decrease in temperature. So most importantly, we know that we're starting off with the universe being unfathomably small and dense and hot. Smaller than the space between my fingers, smaller than an individual atom. That's the entire universe at this point. And for all of that energy to be concentrated in on that single point source, it has to be incredibly, unfathomably hot. So 1 microsecond after the Big Bang, 1 fraction of a second after the Big Bang, the universe has expanded to something maybe the size of the Earth's orbit. So it's expanding fairly rapidly. That's an understatement, certainly. And temperatures are still incredibly hot. And the most startling thing that happens here is that they're actually too hot for atoms to form, too hot for stars to form. So the entire universe at this point is really just pure energy. And so one way to think about the relationship between energy and matter here is in terms of the conservation of energy. We think that the total amount of energy present in the universe is the same as at the moment of the Big Bang. So all of that energy is just packed into a smaller and smaller and more dense area. So that means that temperatures have to be much, much higher. So the entire universe at this point is like some exaggerated version of the core of a star. E equals mc squared is basically just going on all over the place. And it's too hot for fusion, too hot for stars to form, too hot for individual atoms to form first. One thing that does happen is that these very, very small subatomic particles called quarks are finally able to combine at this point to form some of the first subatomic particles that we've heard of, things like protons and neutrons. So some of the first matter, in a sense, is forming, but we're still a little while away from being able to form atoms. We have to cool temperatures. In order for that to happen, you need further inflation to take place. You need further expansion. With more expansion, temperatures continue to cool off over time. So now let's jump forward in time 3 minutes after the Big Bang. The size of this is much, much bigger, and there's really no knowing exactly how big the universe is at this point, but I might speculate that it's as big as the galaxy at this point. Temperatures are still too hot for fusion and too hot to actually form individual stars, so the universe is actually still dark at this stage, but you still have all of this energy being converted into mass being converted into energy, all of this wonderful chaos that's eventually going to allow for the first atoms, and the first atoms are going to allow for the first real forms of fusion and so on. About a quarter of the total amount of protons that were created in that very first step are going to combine together through processes like the proton-proton chain, the process that's undergoing fusion in stars, to form the first helium nuclei. But we still don't really have atoms yet because temperatures have to cool off a lot further for atoms to form. Atoms are not just composed of protons and neutrons, but also all of these electrons that orbit around those protons and neutrons. And the universe is still too hot and dense for that to occur, even 3 minutes after the Big Bang. Now, as we jump forward in time again, as we go from 3 minutes after the Big Bang, so we're still in those first few seconds on the cosmic calendar. If we jump forward in time to around 400,000 to 500,000 years, or 500,000 years after the Big Bang, then expansion is going to take place to form the first cool enough temperatures to form the first real atoms. So you have whole, complete atoms composed of protons, neutrons, and electrons. And those first atoms are really going to be a crucial step in eventually allowing for stars to form. But that's still going to come a little bit further into the future. The other really cool thing that happens is that cosmic microwave background radiation that we talked about, that is evidence of the Big Bang, that is residual from this point in the history of the universe. That when we actually look back to that wall at the edge of the observable universe and see the cosmic microwave background radiation, we're seeing back to not actually the moment of the Big Bang, but this point a little while after it. But this point would not have been reached without all of those earlier stages and this inflation from a single point source. We still don't know what created that single point source and where that energy came from, but we can at least detect it at this stage, 400,000 to 500,000 years later after the Big Bang. About 100 million years after the Big Bang, So we're jumping forward pretty significantly in time here. We would still be in the first couple of days on the cosmic calendar. We have the first stars forming. So the universe has to expand outwards to this point where temperatures are cool enough for the clouds to form, and those clouds then have to collapse back in on themselves to form stars. So it's really strange to me that this process that is really involved in having high enough temperatures to form stars requires cooling down temperatures first. You have to expand, cool down temperatures, cool them down so that collapse can happen. Gravity causes those clouds to collapse in on themselves and you form stars. But the universe is at this stage small enough and dense enough and hot enough for those stars to be the highest mass stars possible. These are the O and the B type stars in the stellar classification spectrum. These are the stars capable of going through the fusion of sulfur and silicon and iron and generating all of the heavy elements that are so abundant on our planet. And without these first generation of high mass stars, we wouldn't have those heavy elements. We wouldn't have the heavy elements that compose our body and our planet and so on. Now, this is when you have cool enough temperatures to finally form a star without that star just blowing itself up. So this is really the first moment where you can form stars. And right in there with this first generation of stars, you also have the first semblance of the formation of galaxies. Because gravity is not only going to allow for the collapse of clouds into these stars, it's going to cluster these gas clouds into disks. And where these stars form, you're going to have this orientation where all these stars are orbiting around a center of mass. So this could be the origin of where our supermassive black hole came from, one of these early generation stars located fairly close to the center of the Milky Way galaxy that went through its short lifespan, maybe only a few million years of being a main sequence star, before it eventually died out, creating a black hole and enriching the galaxy with all that leftover gas. Then the next generation of stars can form from its remnants. And that matter locked up in the core that collapsed down to form that black hole would have accreted more material over time and turned into this supermassive black hole, this monster at the center of the Milky Way galaxy. So now we finally have the first generation of stars and really the first semblance of galaxies. And those first generation of stars would have lived out their lifespans really, really quickly. They burn very bright, very hot. They run out of their core fuel very quickly. And then they seed the way for the low mass stars to follow. So now I'm really jumping forward in time. I'm jumping from maybe the first couple of days on the cosmic calendar all the way into August or September. Now we finally have the second generation of stars, maybe the third generation of stars, and eventually the generation that would include our sun and our solar system formed from that same material that collapsed to form our star. And all of that material, especially the high mass stuff, was only possible because of the first couple of generations of stars, creating all those heavy elements that are impossible to make in a low mass star like our own. So after a relatively short lifespan with these high mass stars, you start to generate these low mass stars, and low mass stars become the norm. Low mass stars are almost definitely the norm across the universe today. And the high mass stars that we still can see, the really bright stars and other galaxies that we still see today, the crazy thing is they're probably not even there anymore. Because we're looking back in time, we're looking back to a point where those stars were actually possible. They've most likely burned themselves out. Their supernova remnants will eventually catch up with us, and we'll be able to see them eventually for what they are now and not what they were. So the universe is probably at this point populated by stars that are much more similar to our sun or even lower in mass. Things like G, K, and M type stars. But the cool thing about these low mass stars is that, one, they have incredibly long lifespans. Our sun has something like a 10 billion year main sequence lifespan. And that is what makes it possible for life to evolve on a planet surrounding that star. Given the time it took for life to evolve to the point of intelligence on Earth, that wouldn't have been possible around one of these short-lived high-mass stars. Intelligent life to have arisen is something that is really going to require the very long lifespan of a low-mass star instead of a high-mass star. Now, also, in order to form rocky planets like our own, you have to have those heavy elements that were only possible in that first generation of stars. So that's, around 9 billion years from the moment of the Big Bang. That's getting you from the moment of the Big Bang to the formation of our sun and our solar system. And that, of course, happened in history. That happened 4.5 billion years ago from our perspective. So to zoom forward in time, this point now is 13.82 billion years since the Big Bang. And the current configuration of the universe is that we have lots of stellar remnants from those high mass stars. We've got neutron stars and black holes that are concentrating a lot of the leftover, a lot of the mass of some of these high mass stars of the early days of the universe. They're keeping hold of that mass, and they're not allowing that to be regenerated into a new generation of stars. And then we have a lot of stars locked up, or a lot of mass in the universe locked up in the form of these low mass stars with long lifespans. Now, this is the part where things get a little bit tricky. Now, this is the part where we're going to speculate on what the future holds, not just for our own solar system and our own sun, but the rest of the universe as well. So we're about 4.5 billion years through our 10 billion year lifespan in terms of the lifespan of our sun, a low mass star. So we've got another 5.5 billion years to go before our sun runs out of fuel, expands to form a red giant, and eventually ends its days as a white dwarf in a planetary nebula. Then that gas may be recycled, or some of that gas might be recycled to form an even lower mass star. But if you think about this progression of first starting out with temperatures too hot for stars to form, and then the first generation of stars when the universe was smaller and hotter and denser, and then the multiple generations of stars that have followed, including the generation that we're part of now, our sun, then if expansion continues, there has to be some point in the future where too much expansion has continued, has occurred, and too much matter is tied up in things like black holes and white dwarfs and neutron stars for there to be any more stars. So if we speculate about a future in which expansion continues to occur, and in fact, expansion is most likely not only going to occur, but to accelerate in its expansion based on the observational evidence, then we'll reach a point in the future where it will be too cold and too diffuse, the universe as a whole, to actually form stars anymore. Most of the mass of the universe will be tied up in stellar remnants that cool off over time and don't give off any light, things like white dwarfs and black holes, and maybe some of these stars that collapsed and are trying to form won't reach that threshold necessary for fusion to take place and will end their days as these things called brown dwarfs. So eventually, we reach a point where the universe gets too cold and too dark to create light anymore. And then that expansion continues indefinitely. So that's one possible fate for the universe. And what it seems to be locked up in, this idea of whether or not the universe continues to expand or then collapses back in on itself, is what's actually driving the expansion of the universe. This is the big question at the heart of the future of the universe, the big thing in question, the big problem. Prior to the late 1990s and the launch of the Hubble telescope, it was largely expected that the universe would reach some finite size. It would expand outwards. It would continue to expand because that's what we're seeing happening today, and then reach some size where gravity will grab hold and cause the universe to collapse back in on itself. So this is a really appealing idea. You know, when you really kind of stop and think about it, and you think about what, as a human, you sort of want to happen, at least me personally, I really liked this idea of the universe collapsing back in on itself and everything starting over again. You have this beautiful reincarnation. You have this beautiful cyclicity to the universe. So that's what was expected when we launched the Hubble telescope in 1998. We were expecting to see observational evidence that would suggest that the universe is continuing to expand. It's going to reach some finite size and then collapse back in on itself. Because the type of matter that we can see out there in the universe right now would suggest that that's going to be the possibility. There's lots of things causing gravity to be this thing that takes hold of the universe and causes it to collapse back in on itself. So we were expecting to see basically the big crunch, this expansion outwards to a single point, to a finite size of the universe, and then this collapse backwards to essentially the moment of the Big Bang. And then from there, maybe a new universe forms. So personally, I'm very attracted to that idea because it gives some sort of sense of cyclicity to the universe, some sense of reincarnation to the universe, to have it expand out to this point and then collapse and then start back over again. Now, after we launched the Hubble telescope in 1998, we saw strong observational evidence in the form of these most distant galaxies that were finally visible to us, that they are expanding away from us. They are moving away from us at a faster rate than was previously calculated, and a faster rate than they would have early on in the early days of the universe. And so what this basically means is that the universe is not slowing down in its expansion, it's actually speeding up. It's accelerating in its expansion. And if we carry that through to the inevitable conclusion that not only is it expanding, but it continues to expand, then the universe gets too cold and dark for stars to form. It gets too cold and diffuse, low in density, and too much material is locked up in the form of black holes and neutron stars and so on for new stars to form. And then the universe reaches this kind of cold, dark, deathly conclusion. You know, it's not quite as appealing as that big crunch where the universe collapses back in on itself. So the difference between the two, whether the universe continues to expand and actually accelerates in its expansion or collapses back in on itself, depends on what's actually driving the original expansion of the universe to begin with. And that seems to be tied up in this type of matter and this type of energy that we can't observe directly, but we think actually makes up much, much more of the universe than originally expected. This also calls into a question sort of what the universe is actually made of when you actually peel back what atoms are made out of and what things like protons and neutrons are made out of. It could be that there are types of subatomic particles that we just can't really account for and that we don't understand at this phase that are making up some of this dark matter and dark energy. What we can say for sure, though, is that dark matter and dark energy is making up by far the majority of the universe. The empty space is actually not devoid of any kind of substance, but that empty space contains some property that's causing the expansion of the universe to continue and to actually accelerate in its expansion. So dark energy is making up approximately about 72% of the universe, the total amount of energy present there. Dark matter, about 23% of the universe, composed of these things called weakly interacting massive particles, possibly. that only leaves 5% of the universe to be composed of everything that we can actually observe directly, everything that we've talked about in this class, planets and stars and the gas in nebulas, everything else that we can actually see is only making up a very small percentage of the universe. And we might want to call it normal matter, but if it only makes up 5% of the universe, it's not very normal at all. So knowing the total energy distribution of the universe allows us to sort of better understand what will happen in the future, whether expansion continues out indefinitely. So this is definitely not the thought that I want to leave you guys on with today. I want to leave you with a little bit of a better perspective of where we are in the universe and the importance, even given our tiny size, of our planet, of the Earth itself. So the last thing I want to leave you with here is this idea of where we are in the universe. And it's something that Cosmos addressed in calling it our cosmic address. So the basic premise here is that if you were trying to tell somebody where to find you on the surface of the Earth, you would tell them that maybe you live in the United States and that you live in Louisiana. There would be different tiers to your address. And within Louisiana, you live in maybe Covington, and you live on Maple Street in Covington, and so on. Now, that's not going to cut it if you're trying to give directions to an alien on the other side of the universe. You would need to broaden your perspective out a lot and give them your cosmic address. And that cosmic address would put you on Earth, which is the third rock from the sun in our solar system. And our solar system is within the Milky Way galaxy. As you'll see, there are even broader parts to that hierarchy, that cosmic address. So I'll let you kind of cut to this clip from Cosmos and you'll see where we are. See, not only are we located on Earth, Earth is located in our solar system is located within the Milky Way galaxy, but there's even a broader structure beyond that. The Milky Way galaxy is one of 3 big galaxies and a smattering of smaller dwarf galaxies within this group of galaxies, all bound together by gravity, that William Herschel called the local group. So this local group of galaxies is composed of the 3 big ones being the Milky Way galaxy, the Andromeda galaxy, which we will inevitably collide with at some point in the future, and M33, which is called the Triangulum galaxy. In addition to that, there are a bunch of little small galaxies, and all of these things orbit around a common center of mass. The total width of this group being about 3 million light years apart. And that's our approximate distance from the Andromeda galaxy. The local group, composed of those 3 big galaxies and the smaller ones, makes up a bigger structure called the Virgo supercluster. So we have the Virgo group, the Ursa Major group, and so on. You have 5 major groups that make up, including our local group, this Virgo supercluster. And then when you broaden your perspective out even further, you can see that that supercluster is one of countless millions of superclusters of groups of galaxies across the universe. So this is the way our cosmic address would read. We're in the Virgo supercluster, the local group, the Milky Way galaxy, and within the Milky Way galaxy, we're about 3/4 of the way between the center of the Milky Way galaxy and the edge of the galactic disk, around a fairly nondescript sun, a star called the Sun, and we're on a very, very small planet orbiting that sun. And this is enough to really still sort of leave you with this sense of being extremely small and extremely insignificant in the universe. And so the final perspective I wanted to leave you with is turning our attention back towards our tiny little planet. So in 1990, the Voyager 1 probe achieved the distinction of having traveled as far away from our planet as any object had until that point. And it continues to be the furthest object that we've managed to launch out into space. It's just now reaching the very, very edge of the Milky Way galaxy. So it was launched in 1977. In 1990, it was just crossing the orbit of Neptune, and that put it 3.7 billion miles away, or about 30 astronomical units away from Earth. At this time, people like Carl Sagan convinced the operators of the Voyager spacecraft to turn it around and to take a picture back into the inner solar system so that we could not only see how far we have to go, both in terms of our understanding of the universe and in terms of traveling across the universe, but we could also turn around and see how far we've come. And so this one picture is probably the most famous picture from that venture, from the series of pictures taken of the inner solar system at this point. This picture is called the Pale Blue Dot. It was taken on February 14th, 1990, when, again, the Voyager 1 spacecraft was just crossing the orbit of Neptune. Now, it could be a little bit hard to kind of discern what it is that you're looking at in this picture. So you're looking at the tiny, almost imperceptible little pixel of light blue light on the right-hand side of your screen, a tiny little pixel suspended in a sunbeam. In one of Carl Sagan's final works, not his very final work, but in a book that he published in 1994 called The Pale Blue Dot, he included this perspective for us. And this became a really kind of a famous quote in all of astronomy. It's called The Pale Blue Dot.
That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
So it gives you a little perspective on the enduring legacy of Carl Sagan. Written just 2 years before his death, he encompassed this amazing perspective of how much we have to learn and how much we have learned in this perspective of where we are in the universe and the importance of astronomy. I hope you've enjoyed this class. I've certainly enjoyed bringing it to you. And until we meet again, keep looking up.